Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, we've mostly covered what was in the chapter on probability theory, which is chapter 2 of the textbook. But I do want to spend a bit more time just maybe doing some examples of a couple of the concepts that we did and review in case you weren't fully clear on those concepts before we go into chapter 3, which is the start of random variables, which is where it really starts to get some good applications of other mathematics to probability theory. So before we do that, I want to, maybe first by way of review, we'll review some of the most important formulas from probability theory, most important methods. Not the axioms to start with, because they've been done sufficiently, I think. We're going to talk about, first of all, let's talk about the and some of these names are not very descriptive, but in case, this is what the textbook uses and the notes, the multiplicative rule or multiplicative law of probability. The multiplicative rule is more or less saying that you can find the probability of an intersection of events by doing it in any order you like. And as we've seen, so, for instance, with 3 events, you can do it with 2 events to start with, and what we certainly mentioned is in the context of the definition of conditional probability. It is the probability that A happens multiplied by the probability that B happens given A happens. Now, something that would sometimes be called the multiplicative rule. There's nothing temporal or chronological about this ordering. It doesn't have to be that A is an event that in time happens earlier than B or otherwise. The probability is well defined either way, because as you recall, the probability of A given B is defined. So I use colon equals means that it is by definition just the probability that they both happen divided by the probability that B happens. That is the definition. And it turns out that if you just fix B and let that run over all sets A, that is a perfectly good probability law by itself. It also satisfies the axioms of probability. So you can do it this way, or, but of course, the conditional probability is not defined if probability of B is 0. So it's good to have that proviso there. But if they are defined, you can do it in either order, and it has nothing to do with the chronology of which event happens. For instance, there was that example we even mentioned of cloudy tonight, rainy tomorrow as an association. It's perfectly good to say the probability of cloudy and rainy is equal to probability of cloudy tonight and times the probability of rainy tomorrow given cloudy tonight. But it would be equally valid and perfectly true to say it is equal to the probability of being rainy tomorrow times the probability that given it will be rainy tomorrow, that it's cloudy tonight. So the probability doesn't have to be something that actually makes sense from the chronological order. It's still perfectly well defined mathematically. Now, if you have multiple events, once again, you can pick any order. I'm not going to give you all the orders, but you can clearly, by treating B intersects C as a single event, this has to be equal to probability of B intersects C given A. But sometimes the multiplicative law or rule is used to refer to the fact that you can just keep chaining these together. And often that's referred to as a tree diagram. Probability of A, or it's related to, you could draw a tree diagram to illustrate this. And you say, once again, pick the order that is most convenient of the events. To do this, say, well, A, I know the chance that A happens, and given that A happens, I perhaps know the chance that B happens. And given that A and B both happen, sometimes, remember, it's an intersection, but sometimes I don't write the intersection sign. Given that A and B both happen, the chance that C happens. So this should make perfect sense. And the corresponding tree diagram would be, you start from knowing nothing at all, and the tree often refers to the, at each step of the tree you have a complementary an event and a complementary event, or it could be multiple mutually exclusive events as to what can happen. Either A happens or A doesn't happen. Given that, and so to start from nothing at all happening, in a tree diagram it's conventional to write the probabilities above the corresponding segment, and then the multiplicative law of probability will tell you to find the overall probability. You multiply the probabilities along the various line segments. So given that A happens, either you could have B or not B, right? So it's much like you start here to find the probability of an event. You start here. First, does A happen or not happen? You get A or A complement, and those are the probabilities. And then the relevant probability, once you know that A happens, is a conditional probability. This would be probability of B given A. That's the relevant thing to multiply once you've already got P of A. And similarly here, you'd write probability of B complement given A. Okay, and to flesh out the tree, I won't do all levels of the tree, but if you're talking about it's still the same question regardless of whether A happened or not. It's did B happen or not. So that's probability of B given A complement, and that one is probability of B complement given A complement. So those are the 4 possible conditional probabilities in this direction. A reminder is that given A, these are themselves a probability law. So those two have to add up to 1, clearly. Any two, if there's only 2 branches out of a particular node, those branches have to add to 1. Unless you're just omitting branches for brevity. So here I'm going to omit some branches over here so that I don't have to write them all out. But you can continue this to an arbitrary number of levels. Once again, you're asking, does C happen or not? Does C happen or not? And probability of, I won't write them all out. This is C given A and B. This is C given A and A, C complement, given A and B. This is probability of C given A and B. You see the pattern. So this doesn't help so much, C complement given A and B complement. Doesn't help so much when you have arbitrarily many levels, but you can at least see the pattern of it from there. So that's the multiplicative law. When you get to Bayes' rule, now it is just the Reverend Thomas Bayes, but I guess I put the apostrophe there because that's the grammatical convention. So 18th century, I think, mathematician and probabilist who worked this out for the first time, you can, it's about inverting probabilities, as you know, and I'll just do it in terms of 2 events. If you know that B happened, and you want to find out the probability of A, and you only know the probabilities in the other order of conditioning, you would start by saying, well, what's the chance that A happened and B given A? Now on the numerator, remember that's by the multiplicative law of probability, that's another way of saying A and B both happen on the numerator. On the denominator, it should be probability of B. So sometimes we just write probability of B here. And to expand the same thing, probability of A, probability of B given A. And to expand the bottom, often you wouldn't know P of B. There are 2 ways of P of B happening, one with A and one with A complement. So we just do each of those. With A happening, this is the product that you get, A, B given A. And then the other way of it happening is that A doesn't happen. On the denominator, we're interested in all possible ways of B coming out there, and A complement, B given A complement. Okay, and while there is an extension to K mutually exclusive and exhaustive events, I'm not going to write that here, not to extend the revision more than I need to. But clearly you could have, that would be when you had, instead of A and A complement, you would have A1, A2, A3, A4, A5, which are the 5 different ways that B could happen, so long as they're mutually exclusive and exhaustive. Now, a good application of Bayes' rule is, whenever you need to think subtly about conditional probability, but let's just do that thing that I alluded to of a disease with a certain prevalence. Sometimes these words are used, and this will be just an example. Okay, prevalence means the proportion of the whole population that it has. So let's say it's a rare disease. Let's say the prevalence is 1%, and the test for that disease has sensitivity. These are jargon words, I guess, but I'll explain what they mean. Sensitivity 95%. Now, what sensitivity is the probability of a positive test given positive for disease. So that would be a true positive, not a false positive. Yeah. Equals. So let me say disease positive or negative and test positive or negative. That would just be the way that I... and by the way, the prevalence, if we're talking about a probability, the probability would just be averaged over all people in the population. So that's the probability of disease positive. That's what prevalence is. So sensitivity is the probability, given you have a person who has the disease, of a positive test. Probability test positive given disease positive. And specificity is, let's say that's 90% in this case. The numbers are not what matters, the reasoning is what matters. So that would be the probability. Now, this is, sensitivity and specificity are both good. We want them to be as high as possible. So false positives and false negatives are the bad thing. So we want false positive rate small and false negative rate small. So a false negative would be if you were positive and you actually got test negative. So that would be 5%, right? Test negative and test positive have to add up to 1. So I'll even write that. That would mean that the false negative rate would be 5%, because of all the people that you test on average who have the disease, 5% will get a negative that they shouldn't in the test. So that would be the false negative rate for this test. And the probability of a good thing would be if you don't have the disease to get a test negative, that would be the specificity. So that would mean you get a false positive rate of 10% in this test, in this example that I gave. But in general, they're related that way. And what you really want to know is a person tests positive for the disease. And this is a kind of there's a question of interpretation here. We have to think carefully about what this means. What is the probability? So given that they test positive, often, even though this is a conditional probability, it's common in when you're phrasing it not to mention that it's conditional. It's just, you should always write the probability given all the facts that you've been given. But that is, in this context, a conditional probability. What is the probability they have it? Okay. Now, maybe we'll do the calculation first and then discuss the interpretation, because there's a little bit of an issue as to what this actually means. Let's just, calculate first and ask questions later. So probability of disease positive, right, given the probability, even though the question doesn't say it, it's worth mentioning. You have to be able to insert this. It is a conditional probability because it is conditional on the information that you've been given. So you have to insert that for yourself. So conditional on this fact that we've been given, which is T positive. Okay. So now we plug in Bayes' rule, which is, I don't know that order. I don't know how to go from the test to the disease. What I know is to go from the disease to the test. So on the numerator, I have to do both. So I have to first have the disease, and then I have to test positive given the disease positive. So you see that that's the opposite order of conditioning from what we've done here. Have to correct it. So what are the two ways of testing positive? It could be a false positive, or you could actually have the disease. So we've already got the way that you actually have the disease. That's this. Probability of T plus given D plus. And then the other way is that it's a false positive, which is that you don't have the disease. Probability of T plus given D minus. So obviously D plus and D minus are complementary events, but it's just easy to write it this way. So the way that it happens via a false positive would be that part of the fraction. Okay, so we can... The thing you see when you do these kind of calculations is the prevalence that this P of D plus really governs what happens here. It's 0.01. So times something. And on the bottom you're having 0.01. So, by the way, this is the sensitivity up there. So, 95. Oh, excuse me. And on the bottom, it's really the 0.01 and the disproportion with respect to 0.99. You can see it's going to swamp the actual true positives. The false positives are going to swamp them, because even though the chance of a false positive is 10%, the fact that that's small doesn't, it's still outweighed over here. So overall, that's, it's 95 divided by 95 plus, I think that would end up being 990. So it's, I'm not going to give it exactly, it's approximately 9%, I think. So pretty low, even though you've tested positive. And if you just go through it in an algebraic sense, the key thing influencing that is the disease positive. So having done the calculation, just so that everyone knows how to do it, I was a little vague in how if this is really how the question is stated, a person tests positive for the disease, what is the probability they have it? Does anyone have any comment or critique to offer of what the actual number I've come up with? It's correct in one context, certainly. And it comes down to, by the way, probability is just maths, so it's, if you do the calculation right according to the X probability, the maths is always right. It's just what does it mean? So part of it comes down to this prevalence, If this is correct, the P of D plus being 1%, then this calculation follows. It's exactly mathematically unimpeachable. So the question is it really right to say the probability of a particular person being disease positive is 1%? That is true if the person is picked uniformly at random in the population. That's what's, these are things that are known from surveys, that 1% of the population. If you had either a biased sample, which is, well, it could be as simple as I know that the person is a woman. So if the person is a woman and the disease rate among women and men is different, it would not make sense to put in the prevalence among the whole population. You should put the prevalence among women. Or I could know 5 categories about the person, and then to the extent possible, we should use the probability for that cohort. So we should use the prevalence among the relevant cohort. And then finally, a person, it could, I could rewrite that. It could be a specific person. It could be I test positive for the disease, right? I mean, what is the probability that I actually have it? It becomes harder and harder to give a rational answer to that, because you have to assign prior probabilities to me having a disease. What Bayes' rule does is it relates a prior probability to a posterior probability. And I'll even label that. We'll do Bayesian analysis later. But P of A, just P of A itself, is what's called the prior probability. And the posterior, so you always get from the prior to the posterior by a certain factor, which is the factor that occurs in Bayes' rule. And the interpretation of it is I have some information that I already know. Now, if the person was uniformly at random among the population, the prior would simply be that the person is 1% likely to have the disease. If the prior is you're in a cohort, then you would do the prevalence in that cohort, so long as you know it. If it's a very specific knowledge that you have, it becomes a bit more subjective. What is the prior? Before I test positive for the disease, I have some kind of belief about how much I have the disease, and how much I update my belief it's the same factor regardless. It would just be that factor, but So those are some of the issues with interpretation. I'll just say to be fully correct, I'll just say, or to be unobjectionable, this is the case so long as the person was selected or believed to be selected uniformly at random among the population, because then that prevalence is the relevant prevalence, and among the population. And of course, there are populations of different countries. So you always have to think about what your prior distribution is, what your assumption is. Now, in case anyone didn't know the phrase uniformly at random, that means each option. This is uniformly at random is what's relevant when we've been doing combinatorics. Each single discrete person or item is equally likely. Okay, so that's what uniformly at random means. Okay, so that's the end of the example about Bayes' rule. I want to give one other thing with an example. Oh yes, I wanted to do a bit more about what's called... So I'm just reviewing some of the laws which we have done, but just so you get a bit more practice with them. The one which was, I cannot but put it in quotes, additive law of probability. Okay. Yeah, as you know, I prefer to call this the principle of inclusion and exclusion, so pi. Okay. Principle of inclusion and exclusion. So what this says, well, once again, effectively, to find a probability of a big union, right. I'll be vague so that I don't have to write out something that takes several lines. It will be sum of the probability of the, I'll just say, singletons. Okay, so the singletons are AI, A1, A. Minus sum of the probability of the pairs. Okay, AI intersect AJ. Now that's pairs, so I is not equal to J, and we only count each pair once. But plus sum of the probability of the triples, AI, AJ, AK. Once again, count each. The triples have to be 3 distinct items, and you count each of them exactly once. Minus ... Okay, and there is a last term. It doesn't really go on forever, but you can figure out what the last term is. It's just once you've intersected all the sets together. So the last term would be when you're intersecting all the sets at once, and it has either a plus or a minus 1 sign. It depends on whether k is odd or even. Okay, so we're going to, or whether n is odd or even. That's the additive law of probability. We're going to do one example of the additive law. Now, it was the one that was on the notes, but I just think it's nice. The probability that a random permutation, and to be clear, this is a full permutation, of the numbers, so we've got these numbers 1 up to n in order, and a permutation is just rearranging them in some order, has no number in the correct place, in other words, in its original place. So, okay. So this is sometimes called a derangement because it's an arrangement. It's an arrangement that doesn't keep anything in the correct spot. So we can do this using. Okay, but first of all, we have to do our events. It is, by the way, it's a random. Whenever that's said without qualification, that means i.e. uniformly at random. So every permutation is equally likely. Okay, so sometimes we abbreviate. It is, in other words, if you're not given any information what the unbalanced randomness is, then it's probably equally likely to be any item. So a random full permutation has no number in its original place. Let's see AI. This is pretty clearly the event that is of interest. The numbers 1 up to n. So for I being an index from 1 to n is going to be the event. To do an event, it's usual to put braces around it. It's just a quick way of saying that. So I is a number is in the correct place, or let me say original place to be unambiguous. Okay, so that's the event. And the probability of having no number in its original place. Well, I'm going to do the complement. Okay, so this probability is equal to 1 minus. Always do 1 minus probability of the complement if you can't get started. That's always a good idea. So if it's not the case that no number is in its original place, then that means at least one number is in the original place. Okay, original place. Okay, and to do this, so when we say at least one, what set operation is that? At least one of a certain number of events happen. Say it out loud. Oh, no, there wasn't anything there to see. If I have a number of events and I want to say the probability that at least one of those events happen, what set operation I'll do that? Well, I've already, yeah, it is complement of none of them. That's right. None of them would be it's the union, because at least one is always saying A or B or C or D and possibly more. So at least one means, A1 is true, or A2 is true, or A3, or any of the others. It is, of course, the complement of none of them. That's what we've used. And depending how you think about that, that might be an application of De Morgan's laws. Because De Morgan's laws say that the complement of the union is the intersection of the complement. So that's saying A1 is false, and A2 is false, and A3 is false. So A1 complement, A2 complement, A3 complement, etc. So this is 1 minus probability A1 union, A2 union, up to A n. So that's what we have. So I'm going to have to do, so rather than doing, I'm just doing the principle of inclusion and exclusion, but I have to do it after a minus sign. So instead of starting with sum of the singletons minus sum of the pairs, I'm already at 1 minus sum of the singletons, then it'll be sum plus the pairs minus the triples plus the quadruples and so on. So let me just say sum I, since there's plenty to write out, I'll just do this. Probability of AI, okay, plus sum over ij, and those are pairs. Okay, so I'll even put set braces among ij. That should be a pair. It doesn't matter which order. Probability of AI intersect aj. Remember, within the principle of inclusion and exclusion, you have intersections. It's only the principle of inclusion and exclusion says to get a union, you do you add and subtract a whole combination of intersections. Initially just single sets, then intersections of pairs, intersections of triples, so on. So minus sum over triples ijk. Once again, the order doesn't matter, and I want ijk all to be distinct. Probability of ai intersect aj intersect ak. It's probably okay. I'll just say plus dot dot dot. It does terminate with the n tuples. So equals. Now here is the great thing. We can calculate these. Now they're not independent. If they were independent, then the probability of an intersection would be just the product. But that's an easy case. If they were independent, I wouldn't have had to do this to start with. I could have just done the product up the top. So so that's going to be 1 minus. So what is the probability to do AI? I hope you see that all the n numbers are effectively identical. It doesn't matter whether I do A1 or A2, I'm going to get the same probability. The numbers are interchangeable. So the probability that they have the same properties. So let's just focus on A1, right? The probability of A1 is the probability that that 1 is in its original place. So, or indeed, I could do AN, but I'll do 1 is in its original place. So there are n factorial total permutations, and only n minus 1 factorial of them have 1 in its original place, because I can permute the n minus 1 others. Right? So it might be even easier to see if you think about this is also probability of AN. Okay, and it's the same for every I. The key thing that's going to happen is within the sums, all the things you're adding up are the same, because it doesn't actually matter which triple of numbers you are. It is, the probability will be the same. So so n minus 1 factorial over n factorial. That is, of course, 1 over n. But so, and how many i's are there? There are n. Okay. So I'm just rewriting each of these terms. There are n choices of a single term. The probability of that term, that number being in its correct spot, is n minus 1 factorial divided by n factorial. Okay. So it seems like there's going to be a lot of cancellation, but I'll keep these things in so you can see the pattern more easily. And then the sum over the pairs. Getting back to combinatorics, how many pairs are there? If there are n numbers total, n choose 2, certainly. So instead of n choose 2, I'm just going to actually write out what that is. n minus 1 over 2. Okay, there will be a number of ways of writing this out. And then the probability of A1, well, it doesn't matter which one, AI intersect AJ, is actually going to be, I has to be in the right spot, J has to be in the right spot, and the others can be permuted. So this is actually n minus 2 factorial. Those are the ones that can be permuted, divided by n factorial. Another way to see this is that it is 1 over np2. Like this is 1 over np1. It's 1 out of all those different permutations. So n minus 1 over 2, and then, yeah, n minus 2 factorial divided by n factorial. Now, then I'll do the triples. Just to fit it on the page, I'll do the triples here. So the triples, how many triples are there? N choose 3. Right? I'm going to write out, you should be familiar with writing n choose 3 in the best form for evaluation of that, if you just, 3 times 2 times 1. So I'll even just put 3 factorial on the bottom here. I can have 2 factorial on the bottom here. And I might as well even have a 1 factorial down here. It doesn't hurt. 1 factorial is 1. So okay. I have to multiply by, as I said, it's going to be n minus 3 factorial over n factorial. The pattern continues. I'm not going to write out all of them. If you want 3 of them in place, all you have to do is permute the n minus 3 others. And this is the exact... So if you want objects 1, 2, and 3 to be in the correct spot, there are n minus 3 remaining that can go any way you like. That's n minus 3 factorial divided by the total number of permutations, which is n factorial. So this is just a big application of all that combinatorics that we did. And then plus, okay, I'll do one more. n minus 1, n minus 2, n minus 3 divided by 4 factorial times, once again, n minus 4 factorial divided by n factorial. Okay, minus dot. So it continues alternating until the very last term, which is when you have all n. And the great thing to see is every time you do this, the numerator in the binomial coefficient teams up with the numerator in the probability to actually give you n factorial, and there's always an n factorial on the bottom. So I can simplify this. This is equal to 1 minus, you see there's 1 over 1 factorial. In case anyone can't see it, I'll just put the n factorial over n factorial. Each one of these terms has an n factorial over n factorial. And then there's 1 over 2 factorial, n factorial divided by n factorial. So, of course, I'll drop the n factorials to the suite. And so from your calculus course, which I know most of you will have had to have done, what series is this once I cross out this? It might even help if I made it a power series with, instead of 1, I had 1 plus x times x over 1 factorial. Okay, 1 minus x over 1 factorial plus x over 2 factorial, x squared over 2 factorial minus x cubed over 3 factorial. Okay, so I'll do it in this. It's actually e to the minus 1. So you can see that either remembering the series for e to the x or e to the minus x. Recall, because remember, to do a Taylor series, and most Taylor, the exponential Taylor series converge everywhere and are exactly what you want. But e to the x, if you want to write that as a Taylor series, you first do the Taylor series around 0. You do 1 is e to the 0, and then derivatives of e to the x are continually e to the x. So you always get 1 as the coefficient. So 1 plus x divided by 1 factorial plus x squared over 2 factorial plus x cubed over 2 factorial. So you would be, if you're substituting into that formula for this series, that's exact if you continue to all infinity. Now, I should actually have made this one as approximate. The reason it's approximate is I'm not actually summing to infinity. So it is approximately e to the minus 1. But in reality, I should put the last... Okay, in reality, the probability, once again, is equal to, it's actually sum I equals 1 to n. I'm going to put minus 1 to the power I, 1 over I factorial. Okay, so it differs from the true e to the minus 1 because that would be sum from I equals, sorry, not 1 to infinity, 0 to infinity. Okay, so that's kind of a curiosity and interesting. But the funny thing is, you might think it gets very, very unlikely to have nothing in its correct place, as in large, or you might think it gets very, very likely. But neither of those is the case. It remains somewhat likely and somewhat unlikely. It's strictly between 0 and 1. It's about, e is 2.7, so it's about 0.35, 0.4, something like that. Okay, So that's the end of that example of the principle of inclusion and exclusion. It's probably the biggest example we've seen because we've done it to general n, but it's a nice result. Are there any more questions about probability and combinatorics before I go on to random variables? Actually, I have two little notational things that I want to say. I'm not sure whether I define sampling with and without replacement. I'm going to do sampling with replacement first. A sequence of trials. Well, as you know, we imagine we have a bag where we can select one object each time, where each trial is independent. They're independent because once you've seen the first object, you put it back in the bag, and then you're just as likely to see that object the next time, and have the distribution. Well, you know, and is a selection of one, I'll just say outcome uniformly at random. Okay. So it's like what I was saying the whole time introducing probability theory itself. If you keep doing the same experiment again and again and again, and independently each time, it turns out the proportion of times that you would get it a certain object tends to the probability of that object. So that's what sampling with replacement means. And sampling without replacement, it really it comes back to all this combinatorics we've done. Now, its first thing to say about this, it is not independent. Okay, these are not independent trials, and it's quite easy to see why the trials can't be independent. Once you've taken out the first outcome, it can't happen again because you do not replace it in the bag. Each trial selects one outcome uniformly at random among those remaining in the bag. Okay, so you imagine a bag of all the possible outcomes. Each time you take out that outcome, and you don't put it back in the bag. So clearly they're not independent. To answer questions about that, you'll have a lot of factorials involved because there'll be n outcomes the first time, n minus 1 the second, and so on. So generally, without being too precise about that, you answer those using all the combinatorics that we've learned. If you have a question about sampling without replacement, that's you'll pretty much have to use counting methods to do it. Okay, so the final thing I wanted to talk about was, particular type of events, and this is really the start. I'm effectively starting chapter 3 here. So, for the moment, it's not a really standard word, but we're going to say a numerical event is an event of the form n is in S, okay, where n is a random number. Okay, we're going to talk a bit more about what that means in a moment. And S is a set. Okay, so those are frequently what we want to talk about. Those. Frequently we'll want to talk about that sort of event. We've even talked about random numbers before, like when I talked about heads and tails. It might even be worth reviewing the thing I talked about last time, because, okay, it is an example of a numerical event. And I talked about having a independent events that were not... oh, yeah, okay, I've got it here. By the way, I annotated a little bit more on the lecture notes from last time. I really want you to be aware that for some reason these are listed as events. Of course, R given C is not an event. An event has to be a set of outcomes. So when you talk about probability of R given C, R is the event. C is a bit of extra information that is used to condition your probability. There's no such event as R given C. The set of outcomes you're looking at there is the same set of outcomes, R, as before. It's just you're doing it in a tilted probability, a different probability, which is using the new information that C happened. And same for R given C complement, C given R, C given R complement. So those are not events. Okay, getting back to the example from last time, which happened a little bit quickly, was 3 fair coins, X, Y, and Z. I was cheating a little bit when I said Z equals X plus Y mod 2, because how do you add up H and Z? But clearly I mean, like, say H is, in this example, I guess I meant that, so H is going to be 0 in this example, and T is 1. So then if you add them up mod 2, that gives you 0 if they're the same number and 1 if they're different numbers. So if they're the same number, then I'll make Z ahead and T a tail. Now, I just wrote those things down. You do have to check that, right? So to check an independence, you check that the probability is multiplied. But in fact, the probability that X and Y are both heads is 1/4. The probability that X and Z are both heads is 1/4. The probability that Y and Z are both heads is 1/4. So each of them multiplies in the way that you expect. But nevertheless, these are not mutually independent coins. For mutual independence, you would have to be able to glean no information about one subset from another subset of the coins. So there's no bleed of information between the two. And that's clearly violated here. If you know X and Y, you know everything about Z. In fact, if you know any two of them, you know the other one. So not mutually independent. And you'll see all the stuff about... So these are actually good prototypes of random variables, even though they're very simple ones, because they take either the value 0 or 1. So now, although I talked about random number, we're going to now give a more precise notion of this called a random variable. So what does it mean to be a random number? It should be a number that is an outcome of an experiment. So we've already talked about some numerical events. By the way, for die rolling, we've even done some of those. We talked about some numerical events. So e.g., if you had a die roll, we had that event D is even, right? For a die roll. We already talked about this kind of thing. That was one event. And D strictly greater than 3. Okay? D less than or equal to 3. All of these are numerical events. D is a random number, and those are events. So far, so good. Now, why am I going to use random variable? I want to be more precise. So much so that I'll give it a new page. Okay. A random variable, and I'm going to be ever so slightly more precise than the notes in the books, just because I hate saying things that are wrong. So a random variable is in layman's terms, it has to be a number that depends on an outcome of an experiment. So I'm even going to say, given a sample space, okay, which I will call omega, and events E, okay, so what are events E? I'm just going to even do a curly E, okay? Just bear with me. Oh, it's really big, isn't it? Okay, curly E. What's curly E for? I'm just thinking of the set of all events. Some people might not like the notion that you have a set whose members are sets. For the purpose of this, you can, if you don't like that, you could call it a family of events. Then you don't have to use the word set. Or you could call it a collection of events. Some people don't like it. Yeah, in set theory, as mathematicians do it, it's perfectly fine to talk about sets whose elements are sets. But if that confuses you, just consider it the collection of all events. And events are themselves, of course, E in E. To be an event, of course, E does have to be a subset of sample space omega. Now, generally you won't come to any harm if you just assume that every subset of the sample space is an event. But technically that's not true. So technically there's only certain questions. It's like the Delphic oracle. There's only certain questions you're allowed to ask and others are banished. But this doesn't affect you. Anything that you really want to ask as a question, yes or no, will be an event. And so given a sample space and events E, the curly set E, there is even a technical term for it that I'm not going to write down. It's called a sigma algebra or a sigma field. Okay. Why sigma? Sigma is a Greek letter which has some kind of connotation with an infinite, countably infinite sequence. So And why countably infinite? Because as you recall, events have to be able to do the third axiom of probability, which is to do with countable lists of disjoint events. And we also want to allow countable lists of events that are not disjoint. So in each of those cases, you have to be able to form the union of a countable list of sets. If that's the case, you can form complements, you can form countable unions. Because of complements and unions, you can also form countable intersections. If that's the case, your family, which is this curly E, is called a sigma algebra. I'm not even going to write that on the page because it's so unimportant for this class, but if you do a measure theory class, that'll turn up. Okay, so those are the events. So it has to be a random outcome, but as we know, as mathematicians, there's a word for something that maps inputs to outputs. That word, the input would be the outcome, right? The element omega of omega. What's a mathematical term for something that maps inputs to outputs? Yeah, function. And I guess it's so important in maths that sometimes the word mapping is used. That's kind of used particularly for people who are squeamish about the word function when the domain is not a real line. This is not a function from the real numbers. The input is not the real numbers. From the sample space, or sometimes called the probability space, omega, to, I'll say, the set of real numbers. The output is always a real number. We often use the abbreviations double-barreled R for this to save writing the set of real numbers. So the input is an outcome. You'll notice I didn't say the input is an event because an event is a set of outcomes. The input is an outcome. So I'll even put, and let's introduce a capital letter X just to give an example. So X of lowercase omega is going to be some real number. So for each outcome there is a uniquely defined real number, omega, in the sample space, which is after all the set of all outcomes. So to be perfectly concrete about this, we could talk about the two dice experiment we talked about. There's 36 outcomes, and then there'll be two random variables that we are particularly interested in, D1, which is the value of the first die, and D2, which is the value of the second die. Those are two random variables. Interestingly, they have the same distribution, but they're not the same variable. So that is the random variable, but unfortunately, in fact I shouldn't have put a full stop, because such that once again, this is, and don't even worry about this, but every numerical event, it's important that we'll work with these events all the time. So the event that X, so X is a random number, the event that it lies in I, I'm going to say this over all intervals, for all intervals I, is actually an event. Okay. So you could write that if you like, X, the event that X lies in a particular interval, and it doesn't matter which interval you want to ask. You could ask, is it between -1 and 1? That has to be an event. You could ask, does it equal 1 itself? By the way, an interval can be a single point. So is in curly E. Okay, that's what it is. Finally, I want to say the distribution. Okay, so that's the end of that definition. This maybe is another definition. Distribution, and for the moment I'm going to define it as information of a random variable. Now, random variable is so common that I call it RV. Okay, so RV, usually with dots, but sometimes I might even write them drops, is the information. The funny thing you might have noticed about the definition of a random variable, it doesn't use P at all. It just uses the space and the set of events. So the probability depends on the probability function, but that probability function tells you the distribution. Probability of the event that X is in I for every interval I. So in order to know the distribution, you have to know everything about the variable in terms of its probability of landing. Okay. But so at the moment it's information. Later we'll find functions that summarize the distribution. For the example that I mentioned of a die, D1 is 1, 2, 3, 4, 5, 6. There's 2 diroles and D2, which is the same. 3, 4, 5, 6. I just want you to note D1, in the context of 2 diroles, D1 is not equal to D2, but they have the same distribution. The distribution, I'll just say, the distributions are the same.